Today we're going to sketch the Bode diagram of a given transfer function with time delay. In order to plot the Bode diagram of transfer function g of s, the first thing we gotta do is set sigma equals 0. For the Bode diagram is a form of frequency analysis, so we're only interested in omega here. The second thing we gotta do is rearrange our transfer function into standard form, which is this form right here. This allows us to easily separate each contributor towards magnitude and phase shift. Also, it makes the corner frequency explicit. The corner frequency is an important value, as we'll see later. Here, it takes on the value of 1/8 radians per second. First, we're going to build the magnitude part of the diagram. In order to do so, we need to evaluate the contribution of each one of the three terms of the function to the magnitude of the output of the system. Our three contributors are the scalar 2, the exponential of -2j omega, and this single real pole located at -1/8. For the first term, since it's a scalar, the absolute value of a scalar is the scalar itself. We're gonna take its value in decibels, so the formula for that is 20 log base 10 of 2, which is approximately equal to 6 decibels. The second term, it's an exponential, and if you are familiar with the polar exponential form of complex number, you remember that this is a number of radius 1 with an angle of -2 omega, so its absolute value is just 1. Log base 10 or any base of 1 is 0 dB. The contribution of the third term is basically just 20 times the log base 10 of its absolute value. The absolute value of this function is 1 over square root of 1 plus 64 omega squared. In order to simplify things, we're gonna use just 3 possible values for this function. When omega is smaller than its corner frequency, we're gonna approximate the function by 0 dB. When it's exactly at the corner frequency, we're gonna use -3 dB. And for omega greater than 1/8, we're gonna use a slope, a descending slope of -20 dB per decade. That's what we have here in the first version of the diagram. Here we can see the contributions of each one of the three terms. The scalar contributes with a straight line at 6 dB. The exponential pretty much doesn't contribute, and the pole contributes with this slope of -20 dB per decade. Now, the good thing about the logarithm is that we don't need to multiply the contributions of each term at each frequency. We can just sum it. So that's what we're gonna do. And here's the result. It starts out at 6 dB, but at the corner frequency it turns into a downward slope. Here we made an adjustment of -3 dB at the corner frequency, as we have mentioned before, and also at 1/10 of the corner frequency and 10 times the corner frequency we made another adjustment of -1 dB. But at the scale, -1 dB is less than 1 millimeter, so it's really difficult to see. But either way, this is the final version of the Bode plot for this g of s. For the phase diagram, it's pretty similar. We have 3 terms and we have to evaluate the contributions of each one of them at each frequency omega. Then all we gotta do is add them up together. That's the beauty of the logarithm. we don't need to multiply things, we just add them. So for the first term, it's just a scalar. It's easy to visualize here in the complex plane that the phase of a scalar which is located on the real axis is always going to be 0. The second term is an exponential, so once again we recall to the definition of the polar exponential form of a complex number, which is magnitude times e to the power of j in its angle. So here alpha 2 is going to be equal to minus 2 omega, but that's in radians and we want it in degrees, so we're going to multiply it by 180 degrees over pi, and that gives us alpha 2 in degrees. The third term is not so straightforward, but with a little bit of algebra we can get to a very concise definition. First thing we do is multiply by j, both the numerator and the denominator, or I if you wish. Then we multiply it by something like, not quite the complex conjugate, but almost that. Then we can get this formula which splits the real part and the imaginary part. We can plot it in the complex plane, and that's easy to see where this formula comes from. It's the tangent of alpha 3. With that in mind, we can build a table with 5 points of interest, 5 frequencies of interest, and its respective angles. Normally things start at alpha and end at omega, but in this table it's the inverse. That's enough for us to plot the diagram. Here we just plot the 5 frequencies of interest and connect them together to form the phase diagram of g of j omega, which is 2 over 8 j omega plus 1 times e to the power of minus 2 j omega. One cool thing that's worth noting is that if we were to plot the Bode diagram for the Bode approximant of our function, which is this one, we would end up with the same graph. We can see that both in its standard form, here we have a pole and a zero that are both real and cancel each other out, and we can see that more easily in the graph. So here we have the pole and the zero, and they cancel each other out, leaving us with exactly the same contributions that we've seen before. In the phase diagram, however, that's a different story. Here in the standard form, we're missing out on the contribution of the time delay. In the phase diagram, that's a very relevant contribution, that's why it's different. In the magnitude diagram, however, the contribution of the time delay was 0, so that's why we get the same answer.